Good morning, Townview. Today we're going to be talking about thermodynamics, specifically exothermic and endothermic reactions. So top of your page, go ahead and write this out. Thermodynamics. Can anyone tell me what thermo means? All right, so thermo is heat. And then what about dynamics? All right, so it's basically change. When we're talking about thermodynamics, we're talking about heat change, heat exchange, but that's really what this chapter is all about. We're going to call from Frisco.
We have to define exothermic.
All right, hold up. All right, so first of all, we need to talk about energy. So what is energy? Everything is energy. Let's define energy real quick. So energy is just the capacity to do work or produce heat. So energy is the capacity to do work or produce heat. Now, what is work? If you took physics, which most of y'all did, you should know what work is. So work is when a force acts on something, causing it to move. So if you were to stand there, try to push the wall for 45 minutes and the wall does not move, was any work done? No. So the only way we could measure work is if movement happened. So if there is no movement, no work is done. You don't need to write that. It's just something you want to know. Next up, we have heat. So what is heat? Heat is an energy transfer by thermal interactions. Examples of that are going to be things like radiation, induction, convection, conduction. So those are our examples of heat transfer. I'm gonna give you all a couple laps and then we'll move on. All right, so next up we have our types of energy. So the first type of energy we have is going to be potential energy. So potential energy is the energy contained within a system because of its position. So that's the definition that you probably heard in physics. Another term we use for potential energy is going to be stored energy. So the way it was probably described to you is if you're standing there and you hold something, for example, a ball, this ball has potential energy. If you drop it, once it hits the ground, that's where it does not have any more potential energy. So its position determines how much energy it's got. Another example would be something like you have a hill and you got something like a boulder at the top of this hill. This boulder has potential energy. You can push it in any direction and it's going to roll down. While it's at the top, it's got potential energy. Once it reaches the bottom and it's got nowhere else to go, that's where it has no potential energy. Next up, we have kinetic. So kinetic, that's just going to be energy of motion. And since we've been talking about kinetic energy, y'all remember kinetic molecular theory? KMT? What is kinetic molecular theory? It tells us how molecules do what? It tells us how molecules move around. In chemistry, when we talk about kinetics, we're typically talking about thermal energy. So how heat transfers. Because what is kinetics? It's how fast something is moving. And what is temperature? What is temperature? What's the definition of temperature in chemistry? It's not heat. Heat is temperature transfer or energy transfer. Hot or cold, but what does it mean at a molecular level? Something is hot. What does that mean? All right, so molecules are moving really fast. So when we're talking about thermal energy, we're talking about kinetic energy. So thermal is a type of kinetic, and then chemical is a type of potential. So chemical is it's a form of potential energy related to the structural arrangement of atoms or molecules. So it depends on the chemical formula that you're dealing with. For example, an alcohol or a gas like CH4. So the chemical structure determines the amount of energy that it's got, and chemical is stored energy, so it's a type of potential. Last one, which we kind of discussed already, thermal. It's a form of kinetic energy resulting from the motion of particles, and it's transferred as heat. So thermal energy, when you transfer it, that's when you call it heat. You good? All right, let's move on. Anyone need more time here? All right, I'll give you all another few seconds. Next up, we have law of conservation of energy, which we've discussed before. We talked about this when we were balancing equations. Law of conservation of energy tells us that the total amount of energy in a closed system is going to remain constant. A closed system is whatever you want to consider a closed system. When we're talking about chemical reactions in chemistry, that's typically what we're referring to when we say a closed system. And it basically tells us that energy cannot be created or destroyed, which means the amount of energy you start with needs to be equal to the amount of energy you end up with. So if we have 10,000 joules on one side, everything on the opposite side needs to add up to 10,000 joules or 1,000 joules or whatever I said before. So you can't add any energy on the product or reactant side. It has to be equal on both sides. So energy cannot be created or destroyed. Energy can only change forms. So we can convert it from motion to sound to light to heat, but we can't just get rid of it outright. Excuse me. So in thermodynamics, the world is divided into the system and its surroundings. You don't need to write that part. So what is the system? The system is the part of the world that you want to study. So if the system is a beaker, then this is your system. Now, what is the surroundings? The surroundings is going to be everything around. So the entire universe is the surroundings. But typically, when we talk about surroundings, we're discussing just the room that that thing is in. For example, if I bring a bunch of ice into this room, what's going to happen to the ice? The ice is going to melt. What's going to happen to the room? All right, you know exactly what happens. So the surroundings get slightly cooler, and then the ice melts. So one of them gains heat, the other one gives the heat away. So in that scenario, the system is going to be the ice, and the surroundings is just going to be the room that the ice is in. Can you say that the cafeteria gets any cooler? No, because we're in a closed system. The room is closed. All right, so next term is going to be activation energy. So I know what you're looking at is a hill with a bunch of grass, but that's not the point of this picture. The point of the picture is just to show you what this section is called. So what is activation energy? Activation energy is the energy required to break the bonds in a reaction for a chemical reaction to take place. So here we have our reactants. This is the reactant side. If this is the reactant side, what's this side called? That's the product side. And the reactant side has more energy. So let's say that here we have 200 joules of energy, and our product side has 100 joules of energy. So basically, in this reaction, we're going to release energy. We're going to release about 100 joules. Now, to release 100 joules of energy, what do we have to do first? What do we have to do first in order to release that energy? What was that? All right, you don't break it down. What you do is you have to add energy to it. So let's say that this is 100 joules. So we have to add 100 joules to this in order to get 200 joules out of it. But the sum of energy that was released is going to be 100 joules. So what is the activation energy? It's the energy required for this reaction to take place. If you don't add this energy, you're never going to be able to remove that energy from that system. So I'm going to show y'all a quick example of what that looks like. All right, so that's the energy required for the reaction to take place. Now our next term is going to be catalyst. Who's heard the term catalyst? All right, I'm going to pause for a sec because I can see that there's a problem because it's a catalyst. All right, so what is a catalyst? It reduces the activation energy. It makes it to where instead of needing to add 100 joules of energy, you can add 20 joules of energy, and then the reaction will take place. Another thing to know about the catalyst is that it will not be consumed. So your catalyst can be reused over and over and over again. So like in Dr. Stone, once he got that platinum, He was able to repeat that reaction as many times as he wanted to because your catalyst is not consumed in the reaction. But what does a catalyst do? It reduces the activation energy, which allows you, which increases the rate of your reaction. And then last thing to know about the catalyst is it will not be consumed. So you can use it over and over and over again. You should have. Catalyst is probably a term that they used in there too. All right, let's keep going. So another thing to know about activation energy is what is the activation energy? It's the energy required to break this bond. So once the bond is broken, that's when the reaction begins taking place. So let's look over here. So energy must be supplied to break bonds. This is something you got to understand. You could write it if you want, but this is something you got to understand. So here we have a molecule, two things that are chemically bonded together. Are they going to detach from each other on their own? No. It takes a lot of energy to break this bond. But we have to add energy. So let's say we have to add 200 joules to make this bond break, which basically means to make two things separate, it costs energy. Over here at the bottom, we have two things that are not attached to each other, and then they attach to each other. When two things bond, when a bond is created, that's when energy is formed and energy is released. So on this side, it's producing 200 joules. So down here, or sorry, up here, you have to give it energy to break a bond, but when a bond forms, an enormous amount of energy is created. Not created, but an enormous amount of energy is released. So energy is supplied to break bonds. Energy is released when chemical bonds are formed. So think about something like nuclear fusion, which we'll get into very soon. When two atoms combine and form something new, an enormous amount of energy is formed. That's why in the sun you have hydrogens bonding together, forming helium. Every time that bond is formed, an enormous amount of energy is released. Some of it released as heat, some of it released as light, and then radiation. So a lot of energy released. Any questions on this? All right, next up, I think our last new term for, no, not really, just a couple more terms. So our next new term is going to be enthalpy. Who's heard of enthalpy? So enthalpy is just another word for heat, and it's we use the letter H for enthalpy. So enthalpy is going to be the total heat content of a system at constant pressure. You don't need to worry about constant pressure. We don't change pressure in thermodynamics. So it's always going to be constant pressure. So it's the total heat content in a system. So over on this side, so everybody look up here real quick. Over on this side, let's say that we have 100 joules. That's our enthalpy. Over on this side, our products, so because we said these are the reactants. Our products over on this side, let's say they have 300 joules. So we add some energy, and then we're able to produce, we have 300 joules of energy. So to calculate our delta H, a bunch of people confuse this with a negative sign. Just know these are just bullets, so you can ignore them. But to get our formula for delta H, which is our change in energy, or our change in heat, we just do enthalpy of our product minus the enthalpy of our reactant. So 300 joules minus 100 joules leaves us with how much delta H? So 200 joules is our delta H. Now, if we look at the one below it, our reactants, let's say they have 300 joules, and then our products have 100 joules. So we're going to do 100 minus 300, and that's going to yield what? How many joules? Negative 200 joules. That's our delta H. So right now, I want y'all to make a T-chart. We're going to draw some stuff later, but for now, I want a T-chart. We're going to put endothermic on one side, and then exothermic on the other side. The first thing we're going to write in our T-chart is going to be for an endothermic reaction, we need to have a positive delta H. Which means if we take our product, subtract our reactants, we should have a positive number. So up here, this is our example of an endothermic reaction. This is what our chart is going to look like. For our exothermic reaction, we're going to have a negative delta H. And negative delta H just means that our reactants, they have more energy than our products, and the chart basically is a chart that goes downward. And it's always going to have an activation energy, so it's always going to have that hump or slope in it. But for endothermic, we have a positive delta H. For exothermic, we're going to have a negative delta H. Okay, so next up we have energy of chemical reactions. So based on the type of energy or heat change involved, we can classify reactions as either exothermic or endothermic reactions. You've already created the T-chart, so let's go ahead and put this under the T-chart. So for exothermic reactions, energy is going to be released, and you need to write that exo means exit. So think of something like a candle, and this candle is lit, and energy is leaving the system. Heat is leaving the system, and it's entering the surroundings. So if I were to turn on a candle in this room, it's going to make the room very slightly warmer. We'll write examples later. You don't need to write burning of gasoline. What I want you to write from this page is that in an exothermic reaction, energy is released. You need to write that exo means exit. Did you? Okay. All right, let's keep going. So next up, we have an endothermic reaction. That's when energy is absorbed by the reaction. Endo meaning into. An example of this is going to be like if we brought a bunch of ice cubes into the room. So if we bring a bunch of ice cubes into the room, let's say we brought one big ice cube into the room. The ice cube is somewhere around 32 degrees Fahrenheit, and the room is somewhere around, let's say 74 degrees Fahrenheit. What's going to happen here? Where's the energy going to flow from, and where's it going to flow to? All right, so is the cold going to leave the ice, or is the heat going to enter the ice? All right, so the heat from the room is going to enter the ice. What you need to know about cold, it's just the absence of heat. So cold is not a thing that moves around. It's the heat that actually moves around. So heat from the room is going to enter the ice, and it's going to it's going to increase the temperature of the ice, causing it to eventually melt. What's going to happen to the temperature of the room? All right, so it's going to go slightly down. So it's going to go from 74 to, let's say, 73. It's not going to change that much, but bringing a big old ice cube in the room, heat is going to be absorbed from the room, making the room slightly colder. So in an endothermic reaction, energy is absorbed by the system. An example of this is going to be like cooking or baking anything. When you put batter in the oven, it's going to absorb a bunch of energy from the oven, causing those chemical reactions to take place, and you have a new product. All right, let's move on. So here's our endothermic diagram. So in an endothermic diagram, here are our reactants. And what do we call this section here? This is our activation energy. Good. So activation energy. I want you guys to go ahead and draw this under your T-chart. So endothermic diagram needs to go in your T-chart. So this section right here, that's going to be our activation energy. And then what do we call this section here? So between the reactants and the products, what do we call this? No clues. What do we call this section here? Between the products and the reactants? It is something you just learned about. Nope. All right, so this is going to be products minus reactants. So what do we call this spot here? It's not enthalpy. It's very close though. It's delta. So it's change in enthalpy. So delta, not delta E, delta H. So the space between them, that's going to be the change. So just keep in mind in an endothermic reaction, it's always going to look something like this. It'll always have a hump for the activation energy, but it's always going to look something like this. So it goes from bottom to the top. All right, let's move on. All right, moving. All right, so for endothermic, heat or energy is taken in and the temperature of the substance drops. So in an endothermic reaction, the temperature of the substance drops and the system feels cold. So think of this like this. Here's your hand. That's your hand. And it looks like a foot now. All right, there's your hand. And we put an ice cube in your hand. How's the ice cube going to feel? It's going to feel cold. What's it going to do to your hand? It's not going to freeze your hand. What's it going to do? All right, so where's the heat going to transfer from? All right, so the heat is going to transfer from your hand to the ice cube. The ice cube is going to slightly melt, so it's going to increase in temperature. What happens to your hand? So it starts off somewhere around, let's say 90 degrees, even though we know it's a little higher than that, the warmth in your hand. Now, let's say it starts at 90. When you hold an ice cube, the heat from your hand is going to transfer to the ice cube, making the ice cube warmer, but your hand becomes colder. So that's why endothermic reactions, they feel cold. Another example is, let's say you go outside on a snowy day, a really cold day, and you find like a metal stop sign. What's going to happen when you hold the metal stop sign? All right, so the heat from your hand transfers to the metal, and what does the metal feel like? Cold. It feels cold. And to the metal, your hand feels warm. Like, just know that's how it works. All right. So here are some examples, the really important examples that you're going to be tested on. First one for endothermic reactions is going to be photosynthesis. So where does photosynthesis take its energy from? From the sun. Another example is a cold pack. So when you activate a cold pack, what does a cold pack do? How does it get cold? Chemical reaction. All right, so it is a chemical reaction, but what it does is it absorbs heat from its surroundings. So in a cold pack, it absorbs heat from its surroundings, basically absorbing heat from your hands, making your hands colder. Next one is melting. We already discussed the melting of the ice cube. Next one is going to be evaporation. I would write these examples, yes. So next one is going to be evaporation. So let's talk about evaporation real quick. So here we have a pot, and our pot has water, and we're heating up the water. What's the water doing when we're heating it up? It's absorbing what? It's absorbing the heat, and when it reaches 100 degrees, what's going to happen? So the water stays at 100, but what does the hottest water do? All right, so it vaporizes. So this is called evaporation. What type of reaction? What type of heat transfer is taking place? All right, endothermic. So evaporation is an endothermic type of reaction. And then last one is going to be baking. That's the one we already discussed. So anytime you put a pancake on a stovetop, has anyone ever turned off the stove and put tortillas on the stove? And then what does the tortilla do? It absorbs the heat that's left in the pot, and the pot gets colder. because it's losing its heat to the tortilla.
Well, I don't think it's a tortilla, right?
All right, let's keep going. All right, so here's what endothermic reactions are going to look like to you. So reactants are going to be on the reactant side, and energy will be here with them. So reactants plus energy will equal products, or reactants plus heat will equal products. Write these down. This is what they're going to look like to you. Let's go. Write them down. So there are going to be 2 questions on endothermic and exothermic on the ACP, which is kind of big. That's how many questions you get on stoichiometry. 2. Those. Another way it could look is instead of energy or heat, it could say 500 joules. But basically, your energy is going to be on the reactant side because you're adding energy to it. All right, let's move on. All right, next up we have our exothermic reaction. What do we call this spot right here? That's our activation energy. What do we call this right here? Delta what? That's going to be our delta H. So our change in enthalpy, which is just going to be products minus reactants. And all of your exothermic diagrams are going to look something like this. So energy starts high and then it ends up low. All right, next up we have our exothermic reactions. So energy is going to be given off, the temperature of the substance rises, and the product feels hot. So think about your lawnmower. After you start your lawnmower, 15, 30 minutes later, what's it going to feel like? It's going to feel really hot. So those are exothermic reactions. The most commonly tested exothermic reaction is going to be combustion. What is combustion?
Explosion.
Explosion, sure. It's anytime you're burning a fuel. Anytime a fuel is being burnt, we call that combustion. So yeah, just know combustion is an exothermic reaction. Another example is a heat pack. So anybody ever seen those heat packs that look like they have a little coin in them?
Oh, yeah. Like little silver things?
Yeah.
Yeah.
So you break it, and then you see a crystallization reaction take place, and then it gets really hot because it's releasing heat. Let me see if I can find a video real quick. So I actually purchased these. I'm just waiting for them to come. All right. So currently at room temperature, it's got that little coin. You snap the coin, and then crystallization takes place. Get them for your parents. Adults like them. So then it gets really hot. Now here's the interesting part about these. This is a reversible reaction. The way to reverse this reaction is you put this thing in boiling hot water, you let it sit for sometimes 15, 20, 30 minutes, and then it goes back to looking clear like this. And then you pop the coin, and then crystallization takes place again. All right, 1 second. But anyway, that's an example of an exothermic reaction. Rusting is also exothermic. Neutralization, also exothermic. And then lastly, the other important one is going to be condensation. So if we have a bunch of really hot steam in the room, and the room is cold, let's say the room is somewhere around, let's say the room's somewhere around 50 degrees. So it's relatively cool, and the steam is somewhere around 100 degrees. What's going to happen to the steam? What's going to happen to the steam? It's not going to just disappear. Where's it going to go? Well, it's already vapor. What is it from? All right. What happens? What happens? What happens with condensation? Shh. What happens with condensation in the shower? What happens to your mirrors? All right. So they're gonna fog up. This steam is going to turn back into liquid, and then it's just going to stick to stuff, making it real wet. So when we're talking about condensation, I'll show you on the next page. Hold on. Focus, please. We're almost done. So what do we have to do with the heat? Do we absorb heat or release heat? You release heat. So the way to go from liquid to solid, you got to release heat. To go from gas to liquid, what do you got to do? What do you got to do? You got to release the heat. So anytime you're going from gas to liquid, liquid to solid, you got to release heat. When you're going from solid to liquid, liquid to gas, you got to absorb heat. So let's go back. All right, and that's it. That's all we got for exothermic. Now we're just going to write what the reactions are going to look like. So both times your energy is going to be on the product side. So it could say heat, it could say energy, or it could say 550 joules. But you have to identify that your energy is going to be on the product side. I hope you're not sleeping.
Yeah, I was keeping him on. If he falls asleep.
I appreciate it. If my principal walks in, man, she'll be pissed. And not at you, at me.
What you said? He said the F word.
All right, let's move on. All right, y'all need to be polite. I got a camera here, or a microphone that's hearing y'all. All right, let's move on. Okay, so here we have two examples. What is the first one? All right, endothermic, because our energy is on the reactant side. What's our next one? Exothermic. They're going to be that easy. All right, over here. What's our first one? Exothermic. What's our second one? Endothermic. What's our next one? Exothermic. What's the next one? There you go. So it's going to be a very simple question like that. Which of these four reactions is an endothermic or exothermic reaction? You just got to remember where the energy goes. Energy being absorbed or released. So let's take a look. We're going from solid to liquid, and then from liquid to gas. The surrounding environment, is it absorbing heat or is it releasing heat? It's giving heat. So the environment, the surrounding environment, is giving heat to the solid. What about the water molecules? Are they absorbing or are they giving heat? They're absorbing. All right, so I didn't read the question. What's absorbing the energy? The correct answer is going to be 2. The water molecules are absorbing the energy. All right, in the next one, so in the phase change from water vapor to water and then to ice, so what's happening here? Where is the energy being released? To where is the energy being released?
1.
All right, 1 is correct. So gases, they have an enormous amount of energy. They release the energy, and once they release the energy, they become liquid. And then once they become liquid, they continue releasing energy, and eventually they become solids. So when you're moving in this direction, you're looking at an exothermic reaction. And when you're moving in this direction, you're looking at an endothermic reaction. Any questions? All right, that's our final slide.